Okay, so here we are, still electricity outcome number 2, part 2. Okay, so what we're now looking at is we're going beyond unbalanced charge, and we're looking at electricity within a circuit. So no matter how simple or complex, every electric circuit provides a continuous pathway or loop for charges to move. So important to electricity follows the path of least resistance to complete a full loop or a circuit. And there's 4 parts or 4 basic elements, components for any circuit. There is the source of electricity, and that is the source. It could be a battery or an outlet. It could be a generator, I suppose. The conductor is the wire through which the current flows. It's usually copper wire. In the past, they actually used to have aluminum wires, but the aluminum would get brittle over time, so copper is better that way. The load is the item that changes electricity into some other form of energy. So it could be a light, it could be a motor, it could be a heater, it could be a speaker. There's lots of other different possible loads as well. And then a control is a switch or a device that can turn the electric circuit on or off. And so here we have a simple circuit diagram, and you can see there's a load. In this case, it's a light bulb. The conducting wires are represented by the wires. And you'll notice they're all 90-degree turns. And that's because we have circuits that are diagrams that are very complex and have hundreds of pathways. And so if you don't put a 90-degree turn and bend on it, it's hard to follow where the wire is going. There's your source of electricity. It's a 2-cell battery. And there's your control, your switch that is in the open position. So here are the parts in, when we do circuit diagrams, we have our own kind of symbols and language that we use. And so there's a cell, the long bar and the short. This is a 2-cell battery. The long side is always the plus side. The shorter side is the minus. So over here, this is a 4-cell battery. Okay, so 1 cell, 2 cells, 3 cells, 4 cells, and the big side is plus, the small side is minus. That's a symbol for a lamp. There's a resistor. There's a switch that's in the open position. That is a switch that's in the closed position. Here's a galvanometer used to measure weak current. Here's an ammeter used to measure stronger current. Here's V is the voltmeter, and that's used to measure voltage. This down here is a resistor. You'll want to add it in. This is a variable resistor where you can actually slide a contact point and either put more or less resistance into it, kind of like the dimmer switch for the lights in your house. And that is the symbol for a motor. And so if we look at this circuit diagram up here, you can see we have 3 light bulbs, 2-cell battery. There's my switch. It could be open or closed. And there's my conducting wires. Okay. And there's one pathway. Here is another circuit. There's a motor and a variable resistor, which means I can control how fast or slow the motor is going. There's an ammeter to measure how much current is flowing. There's my switch, which is in the open position again. And there's my 2-cell battery. And for this last one, a parallel circuit, I have a 2-cell battery. I have a motor in one of the branches which is with its own switch, and I have a light bulb with its own switch, and I have another light bulb with its own switch. And here I have a voltmeter. If I want to measure voltage across one light bulb, it's there. And so just so you know, right, there is a pathway for the electricity to flow. Here it is, goes through each of the bulbs, and then comes back here. If the switch was closed, it would come all the way back there, right? Same thing here. Your electricity is going to flow around here. Depending on where your connection is, it'll go there, through the ammeter, and back if the switch was closed. This one's interesting. This one, electricity goes here. If the switch was closed, it would run this motor. And then it could also, at the same time, run up to here if that switch was closed and light up the light bulb too, and it would come back here. And then finally, it could also run here all the way up to there if the switch was closed, light up the light bulb, and come all the way back down to there. So you could actually see in this part of the wire, there's more current going to be flowing than in this part. In fact, 3 times as much current is here compared to there. Now, how do we measure current? First of all, what is current? We use the symbol I for the algebra. It is the amount of charge that passes by a point in a conducting wire every second. So we know charge is in coulombs, so the units for this will be the coulomb per second, or if you want, amps is what everyone else in the world uses, right? And so if you're using like your cell phones, you'd have milliamps going through them. The device used to measure current, to measure strong current, is an ammeter. To measure weak current is a galvanometer. And I am going to show you how to use this in class with a multimeter. So just looking at some of the numbers, radios use 0.4 amps as they're going, and 100-watt lamp uses 0.8 amps, and a color TV about 1.7 amps. That's the old TVs. Toaster 8.8 amps. Look at the big jump. Microwave oven 11.7. Electric kettle 12.5 amps. Electric range 40 amps. What do these four have in common that draw so much current? They all change electricity into heat, and so they tend to draw a lot more current. Now, measuring current is definitely a pain in the amp, which means in order to measure current, you actually have to cut the wires open and then wire in your multimeter. Okay. Now, measuring voltage is a little bit easier. Voltage is, but what is voltage? It's the push and pull of electrons. So current is how much charge is flowing by per second. Voltage is how strongly it's flowing. Okay, it's the push and pull of electrons around a circuit, and that from the separated positive and negative terminals. Electrons are repelled out the minus side and pulled towards the positive side. Okay, and voltage is a term used to describe how strongly the electrons are pushed and pulled around the circuit. And so here we have two circuit diagrams, how to measure current. So here you can see the ammeter is actually wired into the circuit, whereas a voltmeter is actually outside of the circuit and just touching across two points. So I can measure the current that's flowing in this circuit. I could also measure the voltage once the switches are closed. And of course, we will be doing lab work with this in class. And there you can see that's what it looks like in everyday life. If you want to measure amperage, it's actually wired in here. And if you want to measure voltage, you're holding it across and then touching the two parts. Potential difference is another word for voltage. That's the energy difference per unit charge between one point of circuit and another. The units for voltage is the volt. The machine used to measure voltage is called a voltmeter. On your multimeter, it means simply that you're setting it up on the setting for measuring voltage and connecting it into the right spots in the meter. And I'll show you how to use those in class. You can see almost all of your batteries, AA cells, C cells, D cells, they're 1.5 volts. The square batteries for, you've probably seen them for your fire detector, are 9 volts. Household wall plug puts out 120 volts. The big plug that's on behind your stove puts out 240 volts. And in the back of some of your TV sets, there's 200,000 volts going through the voltage supply, so you want to be really careful with those ones. You never open up a TV unless you're qualified to do so. There is a Bill Nye video on current electricity as well. It's available on YouTube, so you can watch it there. We will, of course, we'll watch it in class. So let's do an analogy comparison between this water wheel and this electric circuit. Okay, and so we could see that, water flows through the pipe. Electrons flow through the wires. The valve over here can turn the water on or off. The switch here can turn the flow of electrons on or off. Water goes through pipes. Electrons go through a wire. Work is being done on the water wheel down here. Work is being done on the light bulb down here. Pressure and gravity pushes and pulls the water down. Voltage pushes and pulls the electron around the circuit. The water is flowing, the electrons are flowing. Current is the amount of water that flows by per second. Current is the amount of charge that flows by per second. Okay, and so we've done all that. Of course, here's the point where you would stop and you do your topic 2 questions. Okay, and then topic 3, we start looking at resistance and the movement of charge. Okay, so turns out we need resistance. It's very helpful. Resistance is a property of a substance that hinders the motion of electric charge and converts electric energy into other forms of energy. The units for this are the ohm or the milliohm, and there's a symbol for the ohm. The device used to measure this is an ohm meter. Now, we're not going to deal with the ohm meter part in uh, using the multimeter because we really don't use it very much. Some things you should know that have high resistance: tungsten, that's in the light bulbs, the old, the swirly wire. They have very high resistance. Your space heater or your toaster or the top of your oven, you could see it has something with very high resistance, right? And the high resistance means it decreases current or voltage, and all that extra energy gets changed into heat. So think of resistance as kind of electrical friction. So what causes this? That's when electrons are trying to flow through, but they bump into other atoms. Okay? And so voltage, current, resistance, they're all related. If current is the movement of electrons through a wire, voltage is what makes it move. Then that means resistance is what opposes its motion. Now, a good conductor allows electrons to move very easily, having low resistance. A good insulator doesn't allow electricity to move easily. That means there's a higher resistance. And better conductors have low resistance, and better insulators have a high resistance. And so here's where we get into using your algebra. And so calculations using Ohm's law. So here is Ohm's law. It's here, let's see if I can point to it. That is Ohm's law. Voltage is equal to current times resistance. So V is for volts, I is current measured in amps, R is resistance measured in ohms. So you need to be able to take this formula and manipulate it. Using your algebra skills, if I wanted to, there's my V formula. If I want an I formula, I would divide R out of both sides. So I equals V divided by R. And if I need an R formula, I would divide I out of both sides. And so R is V divided by I. If you're not good at that, that here is the circle that'll work for Science 9. It will not work when you get to the more complicated formulas in Science 10 next year. And so if I need a V formula, all I do is I cover up V, and I have R and I beside each other, which means multiply. If I need an R formula, I just cover up R, and then I have V divided by I. If I need an I formula, I cover up I get V divided by R. So literally, if you have a thumb, you can do this. And this is all the same sort of stuff. And so here is a case where you have to calculate the voltage needed to produce a current of 12 amps over a resistance of 10 ohms. Okay, and so here's how you need to do these. You need to write down I equals 12 amps, R equals 10 ohms, V is what you're trying to find out, so there's a question mark. Okay, and so I need a V formula, so cover up V up here, I get I times R. And then 12 amps times 10 ohms. I just take the numbers from there and substitute them here. And then if I keep the same base units, it just becomes an answer in volts. Okay, so the next one, you need to calculate current. It gives you voltage. It gives you 14 ohms. So over here, I have voltage is 120. Resistance is 14 ohms. Calculate I. So I need an I formula. So I go back up to the top. I cover up I get V divided by R. So that's how that formula comes in. Then I just substitute in 120 divided by 14, and I get 8.6 amps. And it tells me to do it to the nearest tenth. Next one, calculate the resistance of a resistor that has 9-volt battery and current of 2.3 amps. So 9 volts is there, voltage, 2.3 amps is there. Calculate R. So I need an R formula. So cover up R. I get V divided by I. 9 divided by 2.3, I get 3.9 ohms. Okay, and so here are some practice problems for you to try where they give you everything you need and you just have to put in the formula, substitute in, find the answer, and record it with the right units at the end. Okay, and so there is some practice there for you to try and verify. Probably no point in just copying these down. Give them a try, and then see if you did them right. And then there's worksheets that we're going to be doing that you're going to be giving me for marks. And there is, once again, just, oh yes, this was for a lab we're doing to figure out resistance. We don't really have enough time for that, but let's look at resistors. A common electrical component, resistors are designed to have a high resistance to control current or voltage in a device. Now, they change the energy into heat. Okay, and so this is problematic, especially for electronic devices. You want to find a way to get rid of that heat. So that's why computers have cooling fans, so they can do that. And that's why they also have fins on them so they can dissipate heat better. And then we have variable resistors, or otherwise known as rheostats. This is a resistor where you can change the amount of resistance, but it's essentially, think of it as a giant piece of wire, probably nichrome because that's a good resistor, and you have sliding contacts on them, so you can actually increase or decrease the amount of wire that's in your circuit for that by turning a knob, and then that changes the resistance. And then with high resistance, electricity doesn't flow so well, so you can have dim your lights. If you make it really short with low resistance, your lights are bright. Okay, and that's the traditional one. Now, where are these used? They're used in volume controls, speed controls on electric motors. They're used for dimming lights. They're used in surge protectors. They're used in temperature controls. There's all kinds of ones. So here's the old one where it's just a whole bunch of coil and there's two contact points. And then the newer ones actually have different materials that change resistance with how much electricity you apply to it. In all cases, they work on a very simple principle. They can have a sliding contact point that can change the resistance and therefore speed up or slow down the amount of flow, and therefore you can either speed it. In this case, you could dim or make the light more bright. And I also have an ammeter in here to measure how much current is flowing. I have a switch that I can turn it on or off. The shorter this contact point is to here, the brighter the light would be, right? Because there's less resistor in there. But if I want to make this light dim, I would just take this contact point and slide it all the way over to here, and then, of course, there'd be more resistor in, and the light would be dimmer. Circuit diagram, we talked about this already. And there's your circuits. And here's where I am going to probably stop sharing. I just want to see how much is left. I'm going to stop the video there because otherwise it gets way too long. I will do an outcome to part 3 video as well.